Very good afternoon to all. I request all the participants to wait for 1 or 2 minutes. Our resource person will come within 1 or 2 minutes. So please hold on.
Good afternoon.
Good afternoon, sir.
Yeah.
Good afternoon, sir. Good afternoon.
Good afternoon, sir. Shall we start, sir?
Yes, please.
Yes, sir. Very good afternoon to all. On behalf of Mohammed Sadak Management, Principal, Staff, I would like to welcome all the participants from various educational institutions and research organizations for the third day FDP on recent advances and applications of chemical sciences. Today we have the resource person, Dr. Ramesh Gardas, sir, Professor, Department of Chemistry, Indian Institute of Technology, Madras, join with us to deliver the lecture on Benign for sustainable development. First of all, I thank you, sir, for accepting our invitation to be the chief guest. On behalf of Ministry Department, I would like to welcome Dr. Ramesh, sir. Now, I invite Sandhaman Sri, Associate Professor for Chemistry, AJ College Engineering, introduce guest.
Good afternoon, everyone. I take this opportunity to introduce the resource person of this session, Dr. Ramesh Lakshminarayanan Gardas, Professor, Department of Chemistry from IIT Madras. He received his doctorate from Veer Narmar, Gujarat, South Gujarat University. Thereafter, he pursued his postdoctoral research in various universities in the field of physicochemical properties, and applications of ionic liquids from Coimbra University, Portugal, University of Aveiro, Portugal, and Queen's Belfast University, UK. To his credit, he has co-authored 4 patents, 11 book chapters, 7 conference papers, and 4 editorials. He has published 2,000 research papers, which has received more than 8,260 citations. His research focuses much on chemical thermodynamics and phase equilibria of industrially important solvents and their mixtures. Also, he has contributed to the development of non-conventional and environmentally benign solvent systems. In recognition of his outstanding performance as a researcher, Dr. Gardas has been bestowed with several awards by prestigious institutes and societies, including the Mid-Career Research and Development Award 2020 by IIT Madras. Recently, he has been recognized as Associate Editor of an American Chemical Society journal, Journal of Chemistry and Engineering Data, Fellow Royal Society of Chemistry, UK, Asian Thermophysical Properties Research and Significant Contribution Award 2022. The most notable one is that he is featured in the list of world ranking of top 2% scientists in the database of Stanford University, USA, between 2019 to 2022. Thank you.
Thank you, madam. Am I audible and my slides are okay? Moving?
Yes, sir. You are very audible and slides are
Yeah.
presenting.
So, first of all, I would like to thank organizers, including Dr. Balakrishnan and all his team and the entire your institute for giving me this opportunity. So in the next 1 hour or so, I would be sharing our last 13 years of experience, what we are doing at IIT Madras in a generic. And before joining IIT Madras, also I was in this field for a few years. So I'm setting up the talk until 3:15, then we can have some question answer session. So we have 1 hour to go. So please feel free to ask me question at the end. Otherwise, you can send me by email. This is my email ID. And the talk I put with bit generic, benign solvents for sustainable development. So we'll see what is this. As Madam just now mentioned, I am from IIT Madras. We have 34 faculties working on 34 diversified nice areas. So being in Chennai, I welcome you all to come and visit the department and see and promote your BSc and MSc students to take further education in IIT Madras in chemistry department. I would like to thank all my students who are graduated and the students who are currently working. Would like to thank my collaborators in the department, in the institute, and in India and across the globe, and also the funding agencies and today's host institutes who gave me this opportunity to share our work in this online FDP. I have taken some images from ACS, RSC, and UN websites, and some of them through Google. So none of the images I claim the credits. So I just put acknowledge in the beginning itself. Well, what we are doing at IIT Madras and why today I put that title, Benign Solvents for Sustainable Development. Well, our research group at Chemistry Department IIT Madras, we would like to tune the structure of a novel solvent and achieve their properties in a desired manner, and this is for targeted applications. So we tune the structure for a specific properties for a specific application. This structure involves organic nature, inorganic nature, and hybrid also, or we sometimes go for materials. Well, in that we focus mostly on ionic liquids, eutectic mixtures called deep eutectic solvents, and their mixtures with another organic solvents or polar solvent or non-polar solvent or aqueous solutions. And we study their thermal properties, more specifically volumetric and transport properties. We also do study their phase equilibria when they are in equilibrium with another phase, and we generate this extensive data to understand the structure, property, composition relations. And all this we do to have desired applications, how we can replace the volatile organic or environmental, the what do you call damaging, environmental damaging solvents with friendly solvents. So in one line we say our research group strive to integrate fundamental science and engineering approach for the socially relevant, sustainable technological developments. I would like to begin this with this logo. This is United Nations Sustainable Development Goals logo. These are 17 goals. Each one of them is written there. So people say, whatever field we do research, if it can contribute directly or indirectly one of these goals, that is the need of the hour. Well, in a thumb rule, what is sustainable development? People say, whatever today we are enjoying natural resources, we continue to enjoy, but this enjoyment should also be possible for our great grandchildren. And that kind of development is called sustainable development. This is a very crude way, slightly scientific way. There are many definitions. One of the definitions which I like most is the sustainable development is a development which is economically viable. That means the company or the industry should be getting profit. Environmentally acceptable means the government regulations and all this should follow, and the environment should not be damaged, and the socially equitable. So large section of the people should afford. It's not only upper class or upper middle class, but it should be also affordable to even the lower class, and this kind of development called sustainable development. Well, in that, how chemistry can play a role, we'll come back. This is something like a Newton's third law. You protect nature, nature will protect you. You do not care for nature, nature will not care for us. So we have to be a bit careful while doing industrialization and revolutionization or the development, of course, which is necessary. The global chemical industry sales shows, the report was in 2017. It is more than $5 trillion market, and it is expected to become double because it's the fastest growing sector. What chemist can do? A chemist can tell about how to minimize the consumption or how to minimize the generation of materials which are hazardous, or how we can reduce the waste, or how we can convert waste into value-added product. And that's where chemist plays a key role. Those for the days are gone. We don't know the product what we are buying from where it is coming, and after we throw, where it will go. For example, I purchased this mobile. I know this has so many components. From where it came, which country it is, separate parts were made, where it is assembled, and where it is marketed. And if after I use this mobile for 2, 3, 4, 5 years, if I throw, how I should throw, who will take back? If nobody is taking, where it will go? So when this kind of information is not available, it is called a linear economy. But in that linear economy, you say supply chain or chemical supply chain, product supply chain, product life chain, and the global value chain. Each one of them do not know what is happening earlier and what will happen later. But today, to get any industry's approval, circular economy plot is essential, which takes care from the raw materials to production, to the consumption, and to the waste management, and to the recycle, or even after throwing out the product, how it will be put back. So circular economy is the future. Well, we all know we have varieties of the pollutions. Let us not talk about other pollutions, but let's today focus on only solution due to the solvents or due to their what you call high vapor pressure air pollutions. All of us know it is today life is become difficult without this mobile, and average weight of this mobile is not less than 250 grams. There are very few which are less than 250-gram mobiles. That we can keep it in pocket, but we feel or we don't plan to carry one cotton bag or any kind of reusable or multiple usable polythene bags. Every time we purchase a bag or we use and or even let's say you are drinking a cold drinks in a glass, we still ask for straw. Or we are buying a pizza or something, we ask so many knife, fork, everything is a plastic and everything is a single use. Anyway, this is about lifestyle. So the zero waste is a lifestyle. It's not somebody impose on us or teacher will tell us or the government will impose. It is an individual. So any sector, whether it is academia or industry or anywhere, one has to follow this 3R principle for a better lifestyle, not only for our lifestyle, but our forthcoming generations. As much as possible, reduce, reuse, and recycle. The best example is in Indian home style itself. Let's say the one child's shirt becoming a little bit smaller or means child is growing. The mother will not throw that shirt and that will give it to the younger child. After younger child use it and he is growing, then that would be converted this as a what you call a cotton bag. Even after that, it would be used as a what you call for a swiping in a kitchen or somewhere. So it's not about how much we can afford. It is about how much we reuse it or recycle it. That's where we need it. Even after that, using as a kitchen towel, still we can use it, and if it is deformed into the cellulose as some kind of catalyst or some materials. Well, today we'll start why we need to look for alternative solvents, what are this new class of solvents, and what we are doing at IIT Madras in last 13 years. If I can read about the green chemistry definition, it's the design, the development, implementation of both chemical products and the process that either completely eliminate, if not completely eliminate, at least reduce both use and generation of hazardous material. So neither in the beginning of the reaction nor during the reaction, nor even at the end of the reaction, there should be any hazardous substance. And this kind of chemistry can be called as a green chemistry. These are the 12 green chemistry principles. Today we will be talking more on the fifth one, benign solvents. Similar to that, there are 12 green chemical engineering principles. So we must follow. So far we spoke about 17 sustainable development goals, 12 chemical engineering, green chemistry principle, 12 green engineering principles. If you allow me to entire world's research, both academia and industry research, divide into only 3 categories. Let's say solid state research, solution phase research, and the gas phase research. I don't have any doubt that both industry and academia likely to prefer solution phase research over solid state and the gas phase. The reasons are, or the most important reasons are, in a solid state, one has to work on very high temperatures. So the energy requirement is high and the safety protocols has to be followed, and the entire setup or the plants should resist for high temperature. In a gas phase, temperature is also high. In addition to that, pressure is also high. So the leakage problems are there. Whereas in solution phase, wherever mixing, stirring, pumping, transporting, this kind of facilities are required, or this kind of the process are required, it would be more feasible, more easier. So that's where it is. Having said solution phase research is dominant, but they also come up with the baggage of some problems or limitations. Most important among them is their volatile nature. Because of their high vapor pressure, and most of the time these organic solvents have low water solubility, they are the major contributor for many problems, including air pollution, global warming, ozone depletion, climate change, and so on. So one must think how we can avoid this, or at least how we minimize this, or can we look for alternative to this. When you look for alternative, what could be the ideal replacement of this organic solvent? Volatility should be low, chemical and physical stability should be high, recycling should be infinite times or high potential to recycle multiple times, and when we replace with the newer solvent, this should not lead to other complications in chemical plant structure. And for any business model, the cost should be low and the yield should be high. Keeping these things in mind, probably no solvent chemistry would be the better, but it is always not possible. Most of the time people say water-based or the aqueous chemistry, that is also good, but nowadays supercritical fluids, supercritical carbon dioxide and the supercritical water, this research also poor. Well, other than that, few more things are there, I will let you know soon. When somebody is looking for a green solvent, what they are looking, the nature, whether it is protic or aprotic, basicity, whether it is low, medium, high, polarity, whether it is low, medium, high. Not only these many things one will check, but we need a mix and match. Means I need aprotic with low basic, high polar, or I need a protic with high basic and low polar. Like this, the combinations, we need a varieties of the combination, and that's the reason it is becoming more and more difficult to have that one. So if you ask any research scholar, how you choose the solvent, the most easiest question would be whatever my sir told, or whatever my teacher told, or whatever my senior told, or whatever the available in the laboratory rack. Some sensible research scholar will tell, no sir, we will see the liquidus range, temperature range from melting point to the flash point or the boiling point. the temperature range. We look at their functional groups: acid, alcohol, amine, ester, carboxylate, ketone. And we also look whether it is polar or non-polar, or highly polar or highly non-polar. But is this enough? Probably no. While choosing the solvent, because whatever the research we do at laboratory scale, if it gets successful, it will be go for pilot scale and then industrial scale. And that time you cannot say, no, our laboratory scale is with the solvent which is banned, or which is not available, or which is expensive, or which has environmental regulation problem. But then who will scale up that process? So even if it is a smaller scale, one has to keep in mind about the regulatory classifications, legal implications, environmental impact, safety aspect, in addition to their physical, chemical, and biological properties. Well, if you see, most common polar and non-polar solvents used in industry and academia, these are the one. You see the spectrum is almost full. The spectrum, this plot is called Kamlet-Taft plot, polarity versus basicity. But if you see benign solvents, the number of solvents are very less, which not damaging the environment, which are either environmental friendly or the neutral. For example, if you see this box where I am putting my cursor, this is the region where solvent with low purity and high basicity. For example, you want to replace tetraalkyl ethyl ammonium or tetraalkyl butyl ammonium. You don't have any benign solvents. When you don't have anything, how you will tell that industry that don't use this solvent, these are damaging environment? You have not shown the alternative. So it's the duty of the scientist and the engineer fill this spectrum with as many as solvents are possible, and then we can force industry, why don't you use alternative? ACS Green Chemistry come up with solvent selection tool for more than 270 solvents, and they have what you call the parameters to shortlist. You have functional groups. You can choose alcohol, amine, ester, ketone, carboxylate, or whatever, ether, thiol, or you can put a physical properties like density and other things. You put it in the range, or you can choose their principal component analysis or safety aspect or other aspects, even biological aspect. These are the so many parameters you can tune it, and then it will give you results. But the problem is the library is very small. That is only 272 solvents. From the 200, of course, how many solvents you need fill in a process? 1 or maybe 2 or maximum 3 or 4. So the best out of 270 you can choose using this tool, which is free of charge. This website is there. There is another Chem21 public-private partnership company from the Europe. They have published a paper in 2016 on this selection guide for classical and less classical solvents. They have divided industrially important all the solvents into 6 categories and the color code, starting from highly hazardous to problematic to the recommended to the highly recommended. Not only the paper, but they do have an online version using this website. It's very interactive. You can put it in the ascending or descending order of each of these safety aspect or health score or boiling point or the flash point or the family to which the solvent belongs to. And you can just choose the best one because it gives all the parameters with the color. Why? But however, in ACS Green Chemistry is around 270, and in this is also around, in this Green Chem 21 it is also around to 300, not more than that. So overall solvents, we are talking only about 300. But whereas the solvent demand, this is the showing in the petrochemical based solvent demand in 2023 is $57 billion worth market. And this compounded annual growth rate is 4%. So it's keep on increasing. And this is due to the huge demand in 3 or 4 sectors. One is automotive, other one is construction, and the third one is energy. So today the battery industry is booming up, or the electric vehicle booming up, or automobile industry is booming up, or the construction sector is booming up. In all these sectors, solutions and solvents demand is very, very high. However, due to stringent environmental regulation, these companies have been forced to obey the government regulations and forced to look for greener or bio-based or environmental-based solvents which cannot damage environment. One such example is bio-based alcohols, biodiols, limonones, lactates, and ionic liquids, deep eutectic solvents, so on. This is one. Serine is the best example. This is an upcoming solvent which can be replaced potentially in near future with all kind of dipolar aprotic solvents, NMP, DMP, DMF, and so on. Today, the use is less, so this might be expensive, but once mass production comes, this will also become cheap. Today, we are going to talk about ionic liquids. I put a quote here, old wine in a new bottle. Though the topic looks new, which has been old age problems like molten salts, we all know. If I ask you what is the melting point of sodium chloride, salt, which is around 800 degrees Celsius. So the sodium chloride will be in a liquid form beyond 800 degrees Celsius. But we are talking about ionic liquids which are in ionic form and they are in liquid at or nearby room temperature. The history tells in 1914, Paul Warden discovered this first ionic liquid they used to call liquid salt, ethyl ammonium nitrate. That is for Walden has been synthesized this. They were not expecting the salt will be in a liquid form. However, later on, Kenneth Seddon from Queen's University Belfast, his students Tom Welton from Imperial College London, and few others extensively worked in this field. And now, if you see, this field has grown tremendously. The most important reason is this kind of solvent do not have only 1 or 2 or 3 good properties, but they possess combination of varieties of the combination of unique properties. For example, the vapor pressure is very, very low, liquid range is very, very high, non-flammable, electrochemical window is very high, conductivity is very high, and the solution capability of organic, inorganic, or organometallic compounds is very high. We generally call ionic liquids as hybrid salts because in a common salts, both the cation and anion are of inorganic nature. Here, one of the ion, mostly cation, will be of organic nature and the anion would be of inorganic nature. You can see the examples here are heterocycles. Of course, one can have tetraalkyl phosphonium, tetraalkyl ammonium. Anions can be very smaller one like chloride, bromide, iodide, or slightly medium range one, triflate, or even bigger than that, bisphosphonate, and so on. So based on the choice of cation, anion, and alkyl chain length, theoretically, millions of ionic liquid possible. And as I told earlier, very couple of minutes ago, sodium chloride melting point is around 800 degrees Celsius, and the most of the ionic liquids are liquid at room temperature. The structure, if you see, sodium chloride, how closely packed. There is no void volume or anything. Here, there is some space. And this is the predominant region that ionic liquids stay in liquid form. So, if I take a glass of water and I add sodium chloride in it and I stir it, it's dissolved. Can I call this as an ionic liquid? Because I know ions are there inside, because I myself added salt. It is in a solution form. Can we call this as ionic liquid? The answer is no. This is called ionic solution. And when it's solvated happen, these individual ions will be solvated. That's we don't want. Okay, so now we'll go forward. Having said so many positive aspects of this topic, if somebody asks, what are the limitations? Two limitations come forward. First one is the cost. The cost of this kind of solvents usually expensive than the organic solvent, but not all. The study says if you synthesize them in very large scale, like industrial scale, the cost can be comparable. The second one is viscosity. Viscosity of this class of solvents is very high. When viscosity is high, what will be the problem? The problem is wherever you need stirring, pumping, mixing, heating, transporting, the energy required will be high due to the viscosity high. Energy required will be high means cost will further increase. So both is associated with the cost. Then how to address? So we call one arrow, two targets. In Hindi we say ek tir do nishan. So instead of using this ionic liquid in a pure form, can we mix them with existing solvent or water and use that solutions? Why? Cost will reduce, viscosity will reduce. But then where is the question of greenness or benignness? The thing is, if ionic liquid is not used, whatever final product quality and the quantity we are getting for a given raw materials, by using small amount of ionic liquid with the same organic solvents or water, without compromising on final product's quantity and the quality, if we can reduce the requirement of organic solvent significantly, this is also called greenness or benignness. How? The requirement of organic solvent gone down, but we didn't compromise on final product. So this is called using ionic liquid as a performance additive. Now we are not replacing, but we are using ionic liquid as an additive. In this way, the companies, chemical companies also need not to worry that, oh, if we change entire solvent, our entire setup need to change, the process product design setup will be changed, which will be very, very expensive. We don't know it will work or not. Why to take the risk? So that also would be beneficial. Well, while synthesizing ionic liquid, there is a thumb rule. If the cation source Lewis acidity is low and anion source Lewis basicity is low, this combination will be definitely liquid salt or ionic liquid in a liquid form. If both are high, you will get a solid salt. If one is high and other one is low, or another one, first one is low and the second one is high, in that scenario, one has to see the other complex chemistry of the interactions. For one, it is definitely high melting temperature. For 4, it is definitely lowest melting temperature, or it's liquid. One is called ionic crystals, and the 4th one we call ionic liquids. Ionic liquids, the first generation, they were tuning physical properties. How they tune? Based on cation, anion, and cation alkyl chain length. First generation, physical properties like volumetric, acoustic, transport, thermal. Second generation, chemical properties like polarity, dipole moment. The third generation of ionic liquid is biological properties like toxicity, IC50 value. Now the 4th generation of ionic liquids targeting all property at a time: physical, chemical, and biological, which is doable. If you see the applications, about 50 years ago, or sorry, 30 years ago, this field started only using as a solvent or electrolytes. Today, it can be used as in a varieties of the form. Even this review article is bit old, but today you can see much more than this. Not only publications and the patent, even the books also. Not only the books, even the industrial application also. The Mark Shiflett, who was in a Dow company and now he is with University of Kansas, is also the founding editor of Journal of Ion. Can you imagine this field has a journal on his name? Journal of Ionic Liquids. The founding editor of this Journal of Ionic, Mark Shiflett. 3 years ago, this book published, and where up to March 2019, they have summarized the industrial application of ionic liquid. Many of them are at commercial scale, as many as close to 30, and the remaining 30 more are in a pilot scale. In one of the line, he mentioned that the growth, industrial growth on ionic liquid, the way it is growing, very soon the application number would be doubled. That means now it is 60, it would be 120 industrial applications of this field very soon, less than a decade time. He also mentioned there are so many companies, they are using ionic liquids in their company, but would not like to tell because of their patent is in process and they have not received the patent filing yet. So this field not only attracted academia, but it's also attracted industries. However, having said this, thousands of papers are there, more than 50 books are there, so much data is around, patents are around. Still, I believe a lot of the people just devoted in the application part. They just took ionic liquid. If it is working, yes, it is working. If not working, they will go for another one. But the systematic understanding through their structure and property, I'm talking about bulk property, holistic property. This study is lagging behind. And that's where we are focusing, that any research when we do at laboratory scale and you want to expand to pilot scale and then later on industrial scale, one must have their accurate thermophysical property data. So why not we make it in the beginning itself, and that data we'll use understand their insights. So accurate knowledge of these thermophysical properties play an important role on cost-effective design and operation. And these thermodynamic properties Not only determine the feasibility, but also will let you know about the size of the equipment. We need not to have very, very accurate data. If it is, it depends on where you are going to use it. If you are going to use it in derived property calculation, it has to be very, very pure. There are many companies selling this ionic liquid. We never purchase. These are the company list I put: BASF, Cytec, Madras, Solvents, TCI, so on. We have not purchased ionic liquid for 2-3 reasons. First one, purchase means limited library is there. They don't have our choice of cation and anion. Second one, purchased one would be cheaper if we purchase raw materials and spend energy and then dry it and then use it for our research purpose. In this way, the bottle would be 250 ml would be, instead of 25,000, it will become 1 lakh or even more. So synthesized more than 100 new ionic liquids, and also we have re-synthesized more than 50 known ionic liquids. So we have a library of more than 150 ionic liquids. This is the thumb rule, as I mentioned, and it worked most of the time. After synthesizing, purifying, characterizing through IR, NMR, GCMS, or after water content, Carl Fisher analysis, just a second. I'm sorry. Yeah, we'll continue. We have Dr. Balakrishna. We have some 20 more minutes. No, I'll go for some application now.
Yes, sir.
Yeah, 20 minutes you can take. So 3:15, I'll take question answer. So I have some 5-6 applications, but I will go through 2-3 in detail, and remaining 2-3 in quick overview. So I was mentioning that after synthesis, purification, characterization, measuring the property. In a science, any chemistry or any physics or anything you do, physics, chemistry, maths, or what you call biotechnology, or anything you do, engineering, science, when we are conducting our research and noting down in terms of numbers, or wherever quantifying the quality, one has to be very careful. One has to mention about the conditions. It can be temperature, it can be pressure, it can be a moisture, it can be a method, or it can be an instrument, it can be a calibration, or it can be a composition. So the conditions must be mentioned, and when somebody reproduce that conditions as it is, the data should be reproduced. So the crucial one is the sample purity. Some people think that my instrument is costly, so all my results are correct. The instrument is costly, we understand. Sample is not pure. It doesn't matter how expensive your instrument is. If sample is not correct, you will not get results. So the purity of the sample, all this matters. And also you remember, you have error, and you have another error, you have another error. Error will propagate. Only we say that enemy is friend. But in this case, error and then error will not cancel out. Let's say you have a density you want to measure, mass divided by volume. Mass also error will propagate. Error will never cancel out. So this is called error propagation. So one must know at what confidence level the data is presented and what is accuracy. We are happy to inform that more than 87,000 data, 8,70,000, out of that, more than 17,500 data measured in IIT Madras in our laboratory has been included in this NIST, National Institute of Standard and Technology USA, ionic liquid database. Of course, this data is a little bit old, and now it might be slightly more than very close to 20,000 data. Well, I will go through 2-3 application in detail and 1 or 2 application very quickly. So far, whatever I presented, entirely done in our laboratory, like purchasing raw material, designing or before purchasing what kind of cation and anion source we want. So tuning, designing, purchasing, synthesizing ionic liquid, purifying ionic liquid, characterizing ionic liquid, generative extensive database of ionic liquid, and all this we do for a targeted application. And these applications are through collaborations. So these are the last 13 years we have worked on more than or close to 10 different topics. Almost each student will work on different topic. Ionic liquid is common, physical chemistry is common, but applications are different. So this is collaboration with Petroleum Engineering Department, which was in Ocean Engineering Department in our institute. And this fund is funded by Oil India Limited, OIL. So industry is there, one engineering institute is there, and me as a chemist. So the target was how to enhance the dissolution of this tank bottom. What happened with the time? The crude oil settled down and it would be a very hard layer. So the tank cannot be used its fullest capacity with the oil because many things have been settled down here. But settling down is okay. They will keep on using until it will be more than 50% useful. But after a certain time, the operation cost will be more and the usage is very less. So in that kind of scenario, they have varieties of the way of cleaning. They have heating coils. They use organic solvents like toluene to clean. But sometimes they have these tanks itself rotate for speed purpose. But the old generation tanks, which are still in good condition and usable conditions, they don't have these facilities of the coil or heating or this one. Even the tanks which has this facility, every time it is not feasible to clean them. So what they do, manually they go in and dig out. So it is too risky. It looks like it is very hard surface. Suddenly you will see that some soft surface come and entire human can sink. It's very dangerous, and not only dangerous, it is time consuming. People say sometimes to cleaning these tanks, the tanks will not be in use for several months or even sometime for a year. It's a time consuming, it's expensive, it is dangerous, and after taking that crude which is in the solid form, where to throw? It's environmental concern. So to avoid that, people use many things. So we did this as laboratory scale. This is a Oil India Limited project, OIL. They have done the SARA analysis for one of the tank which was closed for more than 1 year. The tank bottom sludge was SARA analysis was done. What we understood from the SARA analysis that large amount of aliphatics and aromatics present in crude oil was bonded by small amount of asphaltene or the resin and not allowing them to dissolve in conventional organic solvent or by heating or by stirring. So conventionally people use toluene or dodecaine or hexane. We don't want to replace that with completely with ionic liquid. We want that to be used, but we want to use ionic liquid as an additive. So we took this tank bottom sludge supplied by Oil India Limited, let's say 0.1 gram. 1 gram of this tank bottom sludge is taken, and we added conventional solvent. Let's say dodecaine or hexane or anything. These are the solvents you can see. Toluene, heptane, decane, ethyl acetate, hexane, individually, not all. So the ratio of tank bottom to the solvent is 1:100. Some tank bottom sludge will be dissolved, not much, very, very, very little. And whatever it dissolved, we do not mind how much it dissolved, because we want to check how ionic liquid will influence to enhance the solubility. So that solubility in organic solvent, we say 0. Then we add 0.1% by mass. So 1 gram crude oil versus 0.1 gram of ionic liquid. Then this is at room temperature. We stir it simply. So further tank bottom sludge will be dissolved. The dissolution part will go up. That concentration we will check through UV visible spectroscopy. And the bottom part, there will be still undissolved. There may be some sand or some other things which is separated, or some undissolved crude oil will be there, which is the bottom part. There the concentration of this aliphatics and aromatic will go down. That we checked with IR and NMR. So with the UV, concentration of aliphatic and aromatic should go up. That we check. And with IR and NMR, concentration will go down. Very simple measurements. Very simple. Even the phase equilibria is even in minutes. Room temperature, less than 1 hour, everything will be over. You stir it at a designated speed and let it settle down, and then to separate, phase it, filter it, and check the concentration. 0 is tank bottom sludge with the solvent. After adding ionic liquid, you see up to 65% enhancement is there. We have checked with a different ratio of stirring, different concentration at room temperature, and a different ratio of crude oil. This is called optimization. Optimization has been done thoroughly. What we observed, more than 60% enhancement observed with small amount of ionic liquid. Sometimes it is less than even 0.1%. That is through UV. And this here, the bottom part where concentration should go down, black one is tank bottom sludge, pure one. Red one is with the pure solvent, and the green one after adding ionic liquid. So here, bending and stretching frequencies are going down, or aliphatic and aromatic concentration is going down, which is also proof. Here concentration going up, that is also proof. And also we have NMR, that is also proof. The peaks for aliphatics and aromatics after adding ionic liquid has been vanishing or reducing. That means the crude oil aliphatic and aromatic part has gone on the top layer. Here We have not replaced this organic solvent, toluene or heptane. We have used same toluene, same heptane. We have added tiny amount of ionic liquid, and the solubility of crude is enhanced 60% more for the same quantity of toluene used earlier. And the results are very promising. What could be the scientific reason? So the possible mechanism would be ionic liquid, either cation or anion or any of them, the lone pair, or ionic liquid will be attacked on the lone pair of the heteroatoms in resin or asphaltene, and then bind with them and make them not to bind stronger with aliphatics and aromatics. So now the resin IL resin bond is more stronger than resin aromatic and resin aliphatic. So the remaining part is done by the toluene. I give example that let's say one strong on a bench, 3 students are sitting. The middle boy is a very strengthy guy or very strong. Put 2 hands on 2 boys' shoulder. Left side one boy, left hand. Right side one boy with the right hand. And he's holding together with tight. Other students are trying to pull out these 2 students, but this boy is too strong. What? Here the middle boy is asphaltene or resin. Left and right boys are assumed saturates or aliphatics and aromatics. And the people who are pulling is organic solvent like a toluene. But one intelligent boy comes, that is ionic liquid, just simply from the backside, pinch on the middle boy's 2 shoulders like this. So the middle boy get just jerk, and the remaining other boys will pull out this one. Well, this is a story, but we believe something similar in chemistry term or in a scientific term might be happening. Further results or further study of computational understanding or the molecular level understanding is required to prove this, but most likely this is what is happening. We proposed and we published, we got patents, papers, student got award, and company is happy. We are happy. Let me go to another example. Enhanced oil recovery. We know that the crude oil primary flooding is a naturally coming. Secondary flooding is they see nearby designated place of the well, they push steam or hot water, and this steam or hot water push the crude oil to the one place, and from there it will come out as a naturally. That is called secondary flooding. But even after secondary flooding, people say more than 30% of crude is still underground. And for that, tertiary flooding will be done, where they pump hot water or steam along with varieties of the surfactants, polymers, emulsifier, and so on. So we want to mimic that. Here it is a sand bed. It is called uniform size silica we have taken, and every time we will push 1 pore volume, 1 PV. 1 PV is around 100 ml. First we will, the sand is a uniform sand is there, that is to mimic the rock underground. We'll push at a designated temperature and pressure. Let's say temperature is fixed this around 353, that is around 80 degrees Celsius, and then pressure is maintained this, or different pressure also we can measure. 1 pore volume of a crude we push, so 100 ml of crude oil we push. Whatever comes out of this, that is called natural flooding, first flooding. After 100 ml crude, we'll push 100 ml of hot water, that is at 80 degree. Whatever crude comes out along with the water, it is a secondary flooding. Believe me, after 2 times pushing, Only first time only crude, second time only hot water. Then the third time, this is the combination with varied hot water along with either surfactant or polymer all together or salt. This is third time 100 ml pushing in a water. So all three together, maximum, we obtain 52%. That means 48% crude is still inside. So the best combination, whatever we achieved without ionic liquid, there we have added ionic liquid, very small quantity, ppm level. It's a 10,000 ppm. This 52 becomes 72 by adding tiny amount of ionic liquid. 20% enhancement crude oil. The secondary recovery was around 45%, only if it is water. In addition to water, if you add this one, this 45 will become 52. But by adding ionic liquid, 45, not only 52, it crossed 72. So this is without ionic liquids, this is with ionic liquids, whereas we gone close to 72%. And this 20% enhancement due to tiny amount of ionic liquids is amazing results. The reason is very simple, no complicated at all. The reason is interfacial tension and the surface tension. The tension or the surface or interfacial tension between hot water or a steam and ionic liquid, or hot water and crude oil, and the angle, the contact angle of the rock and crude oil. So we have measured interfacial tension of water and crude oil. The blue line denotes pure water and crude oil. This is the interfacial tension, let's say around 38 millinewton per meter. Same crude oil, same quantity of water, same conditions. If you add surfactants, it is reduced. If you add some polymers, it is further reduced. If you add some salts, further reduced. But if you add ionic liquid, it has been reduced. So around 38 millinewton per meter interfacial tension dropped down to close to 10. So in most of the case, this reduction was close to 55 to 56% reduction in interfacial tension. And that reduction in interfacial tension is the reason for this 20% enhancement in the recovery. Well, the study need to do further thorough. Even if you are using in small quantity, will this ionic liquid altering the crude oil properties? Can we get back this small amount of ionic liquid and reuse? There are many questions. But the project is over, time duration is over. Student got degree, company got happy, we are happy, we took money and we closed that chapter. Because funds are not there to study that further. I have 4 or 5 more applications, but I will not go in detail. I will just skip through and then I'll give you take-home message. These are radioactive materials, radioactive metal ions, americiums and lanthanides and actinides. This is from DAE or IGCAR lab, where we would like to extract them, lanthanides and actinides, from high-level liquid waste. There would be a large amount of water, mostly in acidic nature, that is HCl, aqueous HCl, large amount of water, and very tiny amount of lanthanides and actinides. Storing them, it would be a huge concern, problem. So can we extract them? Conventional methods are there, dichloroamides and all these things. And the conventional mechanism is solvation. But if you use ionic liquid as a diluent, in addition to solvation, you can also have ion exchange. And due to this, threefold partitioning is increased. Not only partitioning of lanthanides and actinides, but their distribution factor also will be easier. So you can selectively extract lanthanides and actinides. We are also working with the Indo-Spanish project. The project is got over. That can we use ionic liquid in solar refrigerating systems? We were quite successful in that also. I'm skipping that. This was with mechanical engineering. This was with atomic engineers, material scientists. And then this is our own project without any collaboration. Can we have highly polar ionic liquid? Can we use them as a heat transfer fluids? Except viscosity, we designed a new ionic liquid which can be used as an engine oil, which can be comparable with Therminol. This is a conventional or company trade name. All the factors are good except viscosity. But if viscosity is a problem, it cannot be used in engine. I believe soon one can address this viscosity issue and we can have a better engine oil. So no need to replace in months, but it can run for several years in future. We're also worked on ionic liquids as electrolytes in dye-sensitized solar cells, where Gardas initiated this work and did lot, where iodide and triiodide process is facilitated along with this ion. So it can be used as a redox couple, it can be used as electrolyte, it can be multi-purpose. And with some biological teams, varieties of the team. I was telling, no, we collaborate with so many teams. How to extract the bio value added compounds, let's say vegetable waste or let's say some plant based waste or something called chitosan or anything, or even just cellulose dissolution. How we can use this? We have done with the model compounds like tryptophan, caffeine, and now we are also working on dyes removal or the metal ions removal. Let's say even the battery waste. See, now the battery industry is booming up. Electron EV vehicles, yeah, and then EV cars, EV autos, or even the mobiles usage is gone up, or the laptops usage is gone up, where this all batteries will go. Well, varieties of, and we also tried using extraction, desulfurization of model fuel, like a diesel. If it is sulfur content is there, it's a problem. How we can? Everywhere we tried with the industrial collaboration or with different scientific or engineering collaboration, and we went to the proof of concept at laboratory scale has gone. The results can be gone to the next level of pilot scale. So also worked on CO2 absorption and electrolytes in supercapacitors, sensor for varieties of the ions, and the pre-treatment of biomass, and the extraction of micropollutant like pharmaceutical or agricultural chemical waste from how we can extract model compounds, and metal ions from the e-waste, how to do. I know I have quickly gone through on the last 4 or 5, but the take-home message is whatever expert we are, the future is collaboration. Without collaboration, one cannot go from basic, starting from laboratory scale to the industrial scale. Unlike if you want to go for a party or a movie or a picnic, we need a like-minded people. But if you want to grow in science and this one, we need unlike-minded people, where people think differently, people argue, people debate, but respect each other's opinion, and only truth matters. It doesn't matter who is speaking, who is not speaking. It matters what are the results, what is the truth, or what is the scientific basis, how to take it forward, how to fill the gap. So there are many more projects are going on. All the credits goes to dedicated students, cooperative collaborators, and generous funding agencies, and the generous administrator supports, and the institute support. Well, I'll close this here with telling that I strongly believe the world needs to address significant challenges related with energy requirement, be it a battery or be it an electromotive vehicle or anything, environmental related issues, be it a varieties of the pollution, water, drinking water issues, good food issues, health issues. But along with this, you choose any of this topic directly or indirectly related to your research. Keep in mind sustainability. As a chemist, we have to make a difference and we have to play a key role for the sustainable growth and the human or holistic universal problems or the humankind's problems to be solved. Remember, it's not about whether you can afford or not. It's about whether natural resources will be available for all. So always this should be our lifestyle. I can afford every year buying a new mobile. Should I buy or not? I can afford every second year changing a car. Should I buy or not? I can afford to purchase a new clothes every birthday. Should I use it or not? So it should be individual's lifestyle. Let us do our best for our own universe and our own nature and our own great grandchildren's better life. Follow 3R principle: RRR, reduce, reuse, recycle. And innovations can be only possible where scientists and technological come together. And the fundamental science is very, very important. Wherever solvents are there, ionic liquid can replace, because millions of ionic liquid feasible based on the choice of cation, anion, and ionic liquid. The last but not the least, for the young researchers, search, research. In research, one can find alternative for anything. If not anything, at least for many things. Be positive, no negative. Thank you. Thank you all for your patiently listening.
Thank you very much for your wonderful session, sir. I hope the researcher working in different areas and who are willing to work in ionic liquid, they got so much ideas from your presentation. Thank you, sir. Now the session is open for discussion. If you have any doubt, you can ask Professor. He's ready to explain your doubt, clear your doubt. Sir, I have a small doubt. Maybe
Yes,
it's very basic. Being an organic chemist, for a metal catalyzed reaction, how to choose a ionic liquid for a metal catalyzed reaction? Is this possible to choose a ionic liquid for a metal catalyzed reaction?
So, are we doing dissolution, or are we doing leaching, or are we doing extraction? That first we should know. And if it is not ionic liquid, if you are using conventional organic solvent, are you using polar or non-polar or acidic or basic? What could be the pH? In what conditions we are extracting or dissolution? Then similar condition or similar chemical properties we can replace with the ionic liquid, or we can use ionic liquid as a booster performance additive.
Okay, thank you.
So it is always start with the polarity. So if it is a non-polaric nature, we can choose different set of ionic. If it is a polaric nature, you can choose different set of ionic liquid. And if one need to be a very, very low viscous, one set of so it is, if we have enough library and enough understanding now that what kind of functional group, what kind of a starting material can give what kind of properties, especially hydrophilicity, hydrophobicity, and this.
We have to screen a variety of solvents, then only we have to choose.
But no need to screen layers because we do have the knowledge already. Based on, I am telling, for metal leaching for application, what is the requirement of the organic solvent, whatever organic solvent, and that organic solvent's properties we can mimic with the ionic.
Okay. For polar reactions, for polar starting materials, what are the, thank you, sir. Is there any other question?
All are chemists?
Yes, sir. Everyone is from chemistry background.
And all are faculties?
Faculties and research scholars.
So please send me feedback. I'll be happy to answer questions later on also, or if anything is a positive or negative, I don't mind to take it. Okay, some physics people also.
Yes, sir. Yes, sir. Thank you, sir. Thank you so much for your valuable session, sir. Thank you, sir.
Thanks a lot. Thank you all. Have a nice day.
Oh, now we come to the end of our session. A privilege to propose vote of thanks during the day 3 of our online FDP, recent advances and application in chemical sciences. Firstly, I am grateful to Almighty for His blessings throughout this 5 day of FDP. I express my gratitude to our esteemed principal for giving us opportunities to explore and develop. I thank my senior colleague Dr. Balakrishna for his continuous support for this FDP. I wholeheartedly thank our chief guest today, Dr. Ramesh Gardas sir, for your presence and the valuable insights you shared with us. We know more about ionic liquids, synthesis types, and characterization. Thank you for telling you the importance of sustainability also. We got so much information in the blooming research area. We are eagerly waiting to hear from you for the upcoming events also. I express my sincere and heartfelt appreciations to the faculty, researchers from various colleges and institutions. I must also acknowledge our department colleagues for their support and cooperation. Finally, once again, I thank you all. Thank you, sir.
Thank you all. Bye.
Thank you, sir. Thank you, sir.